Hi everyone. Today we're going to be moving on to correlation and regression. This is the final topic for the second exam. So anything after the first exam all the way up through this will be content for the second exam. So again, that includes probability, confidence intervals, hypothesis testing, so t-tests, and then this correlation and regression. And we'll do the same thing as exam 1. On Friday, you can give me any time you would like to take the exam, and I will make sure to have the exam sent over. And I know there may be differences in time zones, so please do specify which time zone you are in when requesting a time to take the exam. And if there's some reason you can't do it on Friday, then anytime this weekend will work also. So please do email me, and I will be sending an email out to the class also. So correlation and regression. Correlation measures how strong of a straight line relationship there is between two sets of data. So measures strength and direction of a linear, that's important, linear relationship between two quantitative variables. Okay, and just like how we have symbols to denote things, correlation is usually denoted with the letter R. Correlation is a number between -1 and 1. 1 meaning a perfect linear relationship with a positive relationship, -1 meaning a perfect linear relationship with a opposite relationship. So what that kind of looks like in a picture, if I draw a scatter plot, something that would look like a correlation of 1 would be like this. If I have points that lie on exactly the same line, so all of these points lie perfectly on the line. I'm off from my drawing error, but so this would be a perfect correlation. Correlation equal to 1. Everything lies on, if you draw one line, all the points lie on that line. Correlation of -1, I'll just go ahead and copy this. If I wanted to talk about correlation of -1, that would look like this, just with a slope in the negative direction. And it doesn't matter what the slope is. It's just a matter if it's a positive or negative. Negative means downward sloping. Positive would be upward sloping, like the example above. So it doesn't matter how steep the incline is. So R equals -1. Correlation is -1 means all of the points lie on the exact same line, and there's a negative relationship. As this variable goes up, this variable goes down. Before, as this variable goes up, this variable goes up also. Now, you get into something like this, where you don't have a perfect linear relationship. Say we had a scatter plot that looks something like this. Actually, I'm going to make my pen a bit more bold. There we go. So, look at this, for example. All of these points don't lie on the same line, right? We see that. There's no one line we can draw that hits all of those points, right? So, this does not have perfect correlation. We do see a general trend, though, that as this variable increases, this one also increases, right? So that tells you that it's a positive correlation. And you know what? If we wanted to make a line to describe this data, it doesn't do too bad of a job. I mean, there's several lines we could draw. Which one is the perfect one? We'll talk about how to do that later. But with a line, we can talk about the relationship between these two variables, sort of. It's not perfect, right? There's some points below, some points above, so it's not a perfect line, but it does a decent job of describing the trend. This would have a correlation of maybe somewhere 0.7 to 0.8, something like that, around that area, correlation. And then similarly, negatives if it was a negative sloping line with, points bouncing around it. Something that would be no correlation would be something that there is no discernible linear relationship whatsoever between the two variables. So you could think like just a random scatter plot. Right? Something like this, there's absolutely no linear relationship between these two variables here, right? There's no line at all that could possibly make any sense to describe this. That line doesn't do a very good job. That line certainly doesn't. That line doesn't. None of these lines can describe this trend at all. How this variable moves according to this variable one way or another. There's no way we can discern that relationship with the line. So this would be an example of no correlation. No correlation means that there is no linear relationship between two variables, meaning there's no relationship with a line. That doesn't mean no relationship whatsoever. Another example of low correlation, so you can have variables that are not correlated but still have some type of relationship. For example, if I looked at something like this, let's draw it like this. Right, look at that relationship. There's no good line I can draw to describe this data, right? For instance, this line doesn't do well capturing this information here. If I draw a line like this, well, that doesn't do a good job at capturing that information. If I draw a line like this, right, that's not really capturing either of these trends. So any way I could possibly draw a line does not describe this data very well. So if you were to calculate the correlation of this, my guess is it would be very close to zero. Not exactly zero. It's hard to get exactly zero correlation. But there is a relationship between these two variables, right? There is a relationship between these two variables. It's just a parabola. It's a quadratic relationship, not a linear relationship. Remember, this only measures linear relationship. So even if you have a correlation that is 0 or very close to 0, that doesn't necessarily mean there's no relationship between the variables. It just means there's no linear relationship. There's no relationship by drawing a straight line. I'm trying to get that curve. So even though two variables could have 0 correlation, there still could be a relationship, just not a linear relationship. It could be quadratic, it could be some cubic relationship like that. It could be something like a sine or a cosine relationship like that. Just anything that's not a line correlation is not the right measurement to study that relationship. And again, and another thing is, if two variables are correlated, that doesn't necessarily mean that one causes the other to happen. For example, if this was the length of your foot, and this was your length of, say, your index finger, your pointer finger. My guess is if I measured these with everyone, there would be this relationship where generally the bigger your foot length is, the longer your index finger is. Those two things are correlated, but they do not cause each other. They don't cause each other. For instance, if your foot all of a sudden grows, that's not going to force your index finger to grow. If your foot gets smaller, it's not going to force your finger to get smaller. For example, if you chop your foot off, don't do that. If you chop your foot off and the length of it attached to you becomes 0, that's not going to make your finger length go to 0, right? Similarly, if you ran over your finger with a steamroller and stretched it out really long and broke all the bones and stretched it out, that's not going to impact your foot at all, right? That's not going to make your foot all of a sudden grow out of nowhere. So these things can change, foot length and index finger, and just because one changes, that doesn't force the other to change. The popular phrase is correlation does not imply causation. If you want to see some more examples of this, you can do a quick Google search. Look up spurious. I think that's how you spell it. Correlations. And it should be the first or the second link that pops up. It'll take you to a website that gives you a bunch of things that have a correlation, but they're very silly things that are correlated, and it doesn't make sense for one to cause the other. So if you have time and you want to be entertained, look that up, spurious correlations, and you'll see a bunch. There's a whole book written on it with a bunch of examples. There's a website that gives you a few of the examples. So look that up when you have a chance. And hand in hand with correlation is this concept of linear regression. Okay, you may see it called as the linear regression line, least squares regression line. Things like that. So essentially what this is this is like your line of best fit. What it says is, for example, if I have this scatter plot here, this example, out of all the possible lines I can make, that line, that line, that line, that line, that line, that line, which one is the best? Best in terms of on average. Let me make one line. Best in terms of on average, if you looked at how far off it was from each of these points. On average, if you looked how far the line was off by from each of those points, we'll call that distance D. What it looks like, what it looks at is if you square all of these distances, if you square how far off it is from all of the points, it wants that total to be as small as possible. And that's how this line works. So remember from an algebra class, the equation of a line, you usually talk about y equals mx plus b, where this is your slope and this is your intercept. In statistics, usually they like to talk about lines in terms of a plus bx, where a is your slope and a is your intercept and b is your slope. This is usually how they do it, and that's because this extends to multiple variables very easily. For example, say we didn't have just one variable x, but several variables x1, x2, x3, so on and so on. You can easily adapt this to a plus b1 x1, b2 x2, b3 x3, and so on and so on and so on. But that is for a different course altogether. So these A's and B's are calculated in specific ways. Some of the things that impact them is the correlation, which in itself is a nasty formula that we're going to use software to calculate. What's also going to matter is the mean of the x values, the mean of the y values. What also is going to matter is the standard deviation of the x values, the standard deviation of the y values. All these things will affect how these are calculated. One line that will always be on the line, or one point that will always be on your line, is the point x bar, y bar. The mean of the x values and the mean of the y values. So if you took these points, let me clean this up. If you took these points, each of these points has, an x value and a y value, right? Different x and y values in each points, but I'm just labeling them all x, y. If you took the average of all of the x values, okay, that's some number. And then if you took the average of all of the y values, I know there are some points that I didn't label. If you took the average of all the y values, that's some number. And if you hunted x bar wherever it fell on the x-axis and y bar wherever that is on the y-axis, that will always be a point on your line, which is interesting. And that's just something that falls out of the process of calibrating your slope and intercept. So let's move to R to work through some of these examples. So we're looking at chocolate consumption per capita and the number of Nobel laureates per 10 million people for 23 countries. So here are the values: chocolate consumption per capita, Nobel laureates. And first, let's make a plot. It's scrunched up, so let's zoom in. Chocolate consumption on the x-axis, Nobel laureate rate on the y-axis. We do kind of see a trend. Generally, as chocolate consumption increases, Nobel laureate rate increases. Again, so there's possible correlation here, but is there a causal relationship? Probably not. To get more Nobel laureate rates, the answer is probably not to eat a lot more chocolate, I would guess. So we do see a general trend. Generally, as chocolate consumption increases, Nobel laureate rate increases also. Let's see what the actual correlation is. To calculate correlation, we use the command cor, C-O-R. Type in the values for the two variables. We have them saved as chocolate and Nobel. And this has a correlation of 0.8. 80% correlation, which is pretty good. So it checks out, right? We said generally it looks like as chocolate consumption goes up, Nobel laureate rate goes up. So we got a positive correlation, right? Positive means that as one variable goes up, the other goes up also. So makes sense, the positive value. It also makes sense that, it doesn't seem like a line would do a terrible job. If I'm kind of tracing a line out with my mouse, it doesn't do a terrible job, right? It does decent for the most part. So 0.8 correlation isn't too surprising here. So let's calculate the line of best fit for this data. So the command to do that is LM. LM stands for linear model. Okay, and the syntax for this is in R. Whoops. You type your dependent variable tilde your independent variable. This is a tilde. What I'm drawing. I know it looks like an N, but that's just my bad handwriting. Okay, so it's LM your dependent tilde your independent variable. So I have Nobel here and then chocolate because I have Nobel on my y-axis here, and that's just the problem didn't specify that, but that's how we set it up. So I'm going to run that, and it gives us the coefficients here, and it specifies which one is the intercept. And if this one's the intercept, that means this one is the slope. So the equation of this line is y equals a plus bx, where a is your intercept. So negative 3.367 plus 2.493 x. Come on. X. There we go. So we can use this line to make predictions. Predict Nobel laureate rate in a country where chocolate consumption is 10 kilograms per capita. So This is predicting Nobel laureate rate. So this is saying that the rate is equal to negative 3.367 plus 2.493 times chocolate consumption. So if we wanted to predict the Nobel laureate rate in a country where chocolate consumption is 10 kilograms per capita, then all we have to do is plug in 10 for this value. So the Nobel laureate rate would be negative 3.367 plus 2.493 times 10. And we can use R as a calculator to calculate that. And that gives us 21.563, remember the units here, per 10 million people. So we can use the line to make predictions with the data. So let's see what this line looks like against the plot. I'm going to save the line. I'm going to call it my line just to save it so I don't have to type it over and over and over again. We saw this plot earlier, right? So next what you see here is this AB line. What AB line does is if you have an existing plot open already, it's going to overlay a line on top of that. So I want to overlay my line on this plot. So AB line will do that. If you type plot instead of AB line, it'll make a new plot that is just the line without the points. But we want to see how the line fits against the points. So when I run that, we see the line is now plotted on the scatter plot. So we can see this is the line of best fit here, and we can see how it looks relative to the rest of the data. And just to show again, if you take the mean of the x values and the mean of all the y values, that's always going to be a point on the line. So if I plot a vertical line for the average of the x values, chocolate, and I plot a horizontal line at the mean of the y values, right? So a horizontal line at the height of the mean of the y values, you'll see that that point, the mean of the x values, comma, the mean of the y values, is a point on the line. And this will always happen. Moving on to the next example, let me clear this. We're going to look at the cars data set. This is a preloaded data set in R. We have the speed of a car versus its stopping distance. How many feet does it take for it to come to a complete stop? If a car is going 10 miles per hour, this is saying that it's taking it 18 seconds to, or it takes it 18 feet rather, not seconds, to come to a complete stop. If you want to know more information about something in R, we can use the question mark command, and it'll bring up all the documentation. We can see all the documentation here. This is data from speed of cars and distances taken to stop from cars in the 1920s. So this was cars 100 years ago, if you can believe that. 50 observations, 2 variables, speed in miles per hour, and stopping distance. And it talks about where it came from and other examples you can do with it. So here's our data. Let's make a plot to see what it looks like. Remember, when you're dealing with a data set with more than one column, you need to use a $sign to specify the column you're talking about. So we're going to put speed. We're going to plot speed on the x-axis and distance on the y-axis. It's yelling at me because it's saying the margins, it's too big for the margins I have. Meaning it's not going to populate over here. It didn't like that. Let me run it again. Now that there's a little more space, there we go. And here's what the scatter plot looks like. We see a general trend. Again, it looks generally like as car speed is increasing, it takes more feet for it to come to a complete stop, right? So that makes sense. Correlation is again about 80%, which sounds reasonable. The line of best fit, remember you do LM and then your dependent variable first, what's on your y-axis first. Stopping distance is on my y-axis, so I'm putting that in here first. And then tilde, squiggly, and then your independent variable, car speed. So the line of best fit for this is, it tells us right here. I'll close this for now. The equation of the line of best fit here is y equals negative 17.579 plus 3.932x. And if you wanted to write that out, that would be distance equals negative 17.579 plus 3.932 times speed. So this is the equation of the line of best fit. Say we wanted to predict the stopping distance for a car going 11.5 miles per hour. So if we wanted to predict the stopping distance, we would plug in 11.5. For x. And we can use R as a calculator to type that out for us. That ends up being 27.639. So we predicted, if we looked at 11.5, which is here-ish, right? We predicted what we think the stopping speed would be. Let's go ahead and plot that all. We'll do the same thing as last time. I'm going to save the line as my line. Make the plot. AB line overlays the line. Okay. So we predicted 11.5, which is around here, I would guess. And we found what the height of that line is. What's the y value of this line at 11.5? Now, when you're making predictions, you have to be careful. You need to keep an eye out for two things. Interpolation and extrapolation. Extrapolation is making predictions outside the range of your data. Interpolation is the complete opposite. Let me copy. Inside. Okay. For instance, let's look here. Our data ranges from here to here. So what is that? 2 or 3 to 26? I mean, we can check real quick, right? Range 4 to 25. Okay. Oops, I accidentally cleared that. 4 to 25. So anything less than 4, the line does not predict very well. Anything above 25, the line does not predict very well. So I wouldn't use this line to predict how many feet it'll take for a car to stop that's going 30 miles an hour or 50 miles an hour. Anything bigger than 25, you're not going to get reliable results because it's not within the range of the data. Same goes on the other end. Anything below 4 is not going to have a meaningful prediction. For example, let's take this line and think about for a moment to yourself what the stopping distance should be if the car speed is 0 miles per hour. If the car speed is 0 miles per hour, it should take 0 feet to stop because it's already stopped, right? But see what happens when you plug in 0 to this line. Distance equals negative 17.579 plus 3.932 times 0, right? This piece is all going to go to 0, right? 3.932 times 0 is 0. So this is going to be negative 17.579 feet, which doesn't make any sense, right? This is saying if our speed was 0, then we need to go backwards 17.5 feet to be considered stop. And that makes no sense whatsoever. So making predictions outside the range of your data gives answers that don't make sense and is not valid. So you want to stick with interpolation. Interpolation is good. That's okay. Extrapolation is generally not okay. Not okay in the sense that it doesn't give you reliable results. And again, we can overlay the mean of the x and the y values and see that that point always lies on your line. So up through here right now is all the material for the second exam. So the probability, the confidence intervals, the t-tests, and this correlation regression will be the content for exam 2. And with this, you should now be able to complete up through homework 7. Okay, so please get working on that. Email me about what time you'd like to take your exam Friday or this weekend, and also your time zone. And please be sure to check which time zone you're in so that we both understand what time you want to take the exam. And then we'll do the same thing as last time. I'll send it over and then have you all send it back in a certain amount of time. All right. Take care, everyone.